Okay, I think we can start. I will give some introduction words. So, good evening, everyone. My name is Stanley Paucar, and I am the president of the SEG student chapter at the Central University of Ecuador. It is a pleasure to welcome you all to this lecture. It is an honor to welcome Professor Pedro de Paula Garcia, who holds a PhD in geology from the Bahia Federal University and spent a year as a PhD exchange student at Queen's University, Canada. He works as the Economic Geology Associate Professor at the Mato Grosso Federal University and is the head of the Geoscience Department at the same university. Professor de Paula Garcia has been working as series editor of the Springer Briefs in Earth Science series and Earth and Environmental Science Library. He worked as a collaborator researcher at the University of Lisbon. He is also a fellow of the Society of Economic Geologists and received the Silver Hammer Prize from the Brazilian Geological Society of Geology. We are pleased to have you, Professor Pedro, with us today to share your expertise. To the attendees, if you have any questions during the presentation, please leave them in the chat and we will address them at the end. Thank you, Professor Pedro. We can start, please.
Hi, good night, everyone. Thank you for being here at this Good Friday, Sexta-feira Santa, as we say in Brazil. And thank you, Stali, and everyone from the SEG student chapter from the university uh, Figepempa. I believe Figempa. I believe is this that we call like Fijempa, okay. Fijempa University, from Quito, Ecuador. Thank you everyone for inviting me, and thank you for having me over here. So, I will have to say everyone that as an editor of both series, as Sally mentioned, is one of my duties to get uh, uh, good quality research to be published with Springer Nature. So if everyone is interested or know everyone that is a good researcher that finishes his or her master's or her PhD thesis and want to publish as a book with Springer Nature, please send me an email. Okay. So we'll talk about South America today, and South America, as we know, is composed of 9 countries. Uh, these are listed 9 countries. Sorry, 12 countries plus one overseas department. There is French Guiana. So these are the 12 countries that we we're listening here. I said 9 countries because these 9 countries are the most important, like Metallogeny, that we'll talk the most. So most of the presentation obviously will be based in Brazil because with be based on my own experience and everything, but also because most of the metallogeny of the South America continent as at all is related to Precambrian shields. They are basically in Brazil and a small part on like the Guianas and Venezuela, I believe, in Paraguay and everything. Most of the mineral deposits are here, and we have like important mineral deposits at the Andes, and we're talking mainly about Chile, Argentina, and Peru as well. But I would talk about ants in general, and I have some stuff in Ecuador. So, um, besides being the place of the most amazing people in the world, South America has about 17.84 uh, square kilometers, and we have like about 5.3% of the world population, that is 438% million people. So when you were talking about mining scenario, we have some countries that stand out as major mineral producers, and we would start to list these countries. We need to talk about Chile as a major copper producer. Is the first. It responds about one third, like 32, 33, 35% of the copper productions, depends on the years you are looking at. And it's the second one in lithium reserves. And we have Brazil that is uh, usually to place in first, but it can be like second uh, in our predictions. It depends, and some years is third, and is first is absolute first in niobium reserves and production, and third in bauxite production, and we have Peru as second in copper production, and sixth in gold production, and we have Argentina is the fourth most largest producer of lithium, and we have Colombia is the fifth in coal exports, and have Bolivia with tin production is really important, and Ecuador that most of you that are listening is emerging as an important copper producer and has a good potential. And we have Venezuela with significant bauxite and gold reserves, and we have like uh, if we need to cite out the other countries, like they have no that important mine operations, but we have gold and bauxite mines in Guyana and Paraguay. We have some locally oriented mining sector, and this Suriname produce gold, bauxite, and manganese, but is just small productions. And like Uruguay, since it's a small country, doesn't have that much of mineral deposits, but it's mainly aggregates and everything. And French Guiana, as I said, is a department, is like a colony of France. It's not a country, and it has like gold and aggregates productions, and there are some no occurrence of bauxite in Niobe and Tantalum. So uh, when we talk about the tectonic of the South America continent, we we need to take a look at the continent and to think about the shields from the oldest to the youngest. So the oldest shields we have like are as I said, they're mainly in Brazilian territory and neighboring countries. So we have like the Brazilian Shield is called in general, and we have like the Atlantic Shield in the eastern part, and the Central Brazil Shield in the central western part of Brazil, and have the Guiana Shield that has northern Brazil and the neighboring countries as Guyana, Venezuela, French Guiana, Suriname, and part of um, Peru as well, and we have Colombia, and we have here part of Bolivia and Paraguay in central Brazil, and those are the parts when you find like basically Archean and Proterozoic rocks, and we have Dungeon chain that is really important, as I said, in copper productions mainly. And we have the Patagonian platform that is a reference more in petroleum than in mineral resources. And we have the Phanerozoic covers that it hosts some of the mineral deposits we'll talk about today, just a small part of it. So today we'll talk besides mineral deposits, as I mentioned out, we're talking in metallogeny and tectonics. So we must emphasize that in the last supercontinent we had that was Pangea, and before that was Gondwana, that was an important piece of Pangea if we count like South America. Brazil was linked to Africa, and we call it as West Gondwana. So this was result from the Neopatriarchal cycle, as we call in Brazil, the Braziliano cycle. And most of South American tectonics refer to this tectonic cycle as Braziliano cycle. So we have, in if we look more deeply, the shields we can divide in cratons. And in Brazil, we have like the two most important cratons are the São Francisco craton. There is in eastern Brazil, mainly Bahia and Minas Gerais states, and have the Amazon Craton that is like one of the is the major cryptonic piece in the South American platform, and we have uh, I would talk about these divisions, but those are the places where you find most of the Archean rocks in South America. The oldest ones are in San Francisco Craton, in Bahia, Minas Gerais, and here close to Pernambuco. And we have another cratons there, the San Luis. There are a small piece that we find here in Maranhão State, and we have some rocks that are under the Paraná Basin that is called the Paranapanema and some others divided. And we have like another kratom that is not represented here. There is like the Rio de la Plata kratom that we find in southern Brazil and Uruguay and everything. And San Francisco kratom was linked to Congo, and San Luis kratom was linked to Western Africa and part of the Amazon kratom as well, as we can see in this cartoon here. So we'll start from the Archean. And if we talk about supercontinents in Archean, uh, we have different interpretations. Actually, as older we get in the geological history of the Earth, we need to consider more factors to understand how the continents were, how was the paleo configuration of the continents. So we have more models, we have more interpretation. So um, sometimes I will show like different models. I won't have time to explain them deeply, as I won't have time to explain like the neural deposit. I'll show it to you like deeply as well, but I'll try my best to do it in the time that I have. Okay, so in Archean, this was extracted from the global tectonics. We have I will not read and everything, but you have like the reference and everything, and I put like in bold uh, like the main of the authors, and you have the complete titles at least the first time that we see it. So you can just take notes if, or you can write. To me, if some of the figures and everything, some of the informations, it gets really interesting, but I won't read anymore. So we have different models to represent what were the cratons or the paleo cratons in the Archean area. We know that all the cratons they have like a Archean nuclei. So we have like the first one, there's the Kennerland solution that we have like the slave, superior, and captal cratons. We can find like captal is South Africa, slave is superior, Canada, Pilbar is Australia. When you have like Filbar, that is like the second solution. There's related to superior Sclavia is like Kefel plus Pilbara, and Sclavia is like slave, Wyoming, there is in North America, there or India, and Zimbabwe, there is in Africa. So, and we have like the likely solution that we have like many super cratons are actually we say like proto cratons. They were like the the first nuclei, the small pores that is initiation those cratons. So we start to talk about the Amazon craton that is really important in South America. As I said to you, it corresponds to about like 30 something percent of the total area of the northern South America. So basically, we have two different interpretations of the the geotectonic, the geochronologic geotectonic province in the Amazon Craton. So the first one that we see here in left is by Santos et al. 2000, and the second one is Tassinari and Macambira 1999. So I will probably refer most to the first one, but basically what we have here, we have like Archean nuclei, um, that it could be called like Carajás or Central Amazonian nuclei, and then we start to have like multiple accretions. Usually they start from the east and they grow up to the west. So we start with Trans-Amazonian province, and then we go like to different names in different province. from so I read like centers that we go like to Tapajós Parima, and uh, we have the Rio Negro province that is only on the northern part, and we have the Rondônia Juruena province. And firstly, the colors are changed here because this is Tapajós Parima. This is not correct in this is figure, so this is correct from this article here. So, and then we have like the Sunsas province, that is the oldest one, that is a meso to almost near Petro's like. So, I will start to talking about the Carajás Mineral Province. Is really important producer, is a major copper and iron producer in Brazil, and it produces a lot of stuff as well as uh, tungsten and gold and palladium and chromium and bauxite and manganese and different commodities. So the Carajás Mineral Province is in the Archean nucleus, the Archean nucleum of the Amazon craton, as we just talked. And it is divided in two domains. The northern one is called Carajás Domain, and then we have the southern one, the Rio Maria Domain. Some works they put also the another domain in the north um, that is not important if we consider the metallogenic aspect. So I will start talking about the southern one, that is the Rio Maria domain, that is the second most important the Carajás domain, and it's like Archean greenstone belt sequence. And in the Rio Maria domain we have uh, basically low gold deposits, organic gold deposits, and we have this rising tungsten deposits that is really important as well. And those organic gold, they are, we can find like deposits and artisanal minings that are garimpos, as we call in Portuguese, and they are related to uh, we have like in the northern part, we have the packages domain that is I just mentioned, but it's not relevant here. But close to it, close to this domain, we have this diadema shear zone that we have a lot of gold deposits that are aligned there. There's, I said, we have Babaçu, Diadema, Kumaru, Sapucaia, a lot of different deposits. And we have this rising here. There is the Pedro Preto deposits, that is when they have like basically what we you would find in a grazing deposit with quartz, topaz, tourmaline, white mica, and molybdenite, and sulfites and everything. So now we'll talk about the Carajás domain that, as I said, is in the northern portion of the Carajás province. And in Carajás domain, different from the Rio Maria domain that is basically greenstone belts, here we have volcanic sedimentary sequence. So there is, it's basically you have different moments of a basin that would not characterize greenstone belts. So you have the Itacaiana supergroup that is basically volcanic zinc iron formation, and you have like a portion of clasts with met conglomerations, clast sedimentation at the top. And we have like really important deposits that are spread in the Carajás domain. So we have important iron deposits that we'll talk later, that they are most concentrated here, that we have like the Serra Norte and the Serra Sul deposits. And we have some gold deposits as Paulo Afonso here, but uh, what really stand out is the iron deposits, iron formation deposits, and the IOCGs that we have. Salobo deposits, there is in Igarapé-Bahia, there is like the northern IOCGs and the southern IOCGs. There is like Alvo 118, Jatobá, Castanha, Bacuri, Sossego, Bacaba, Cristalino, and lots of different. So they really stand out as major copper producers in Brazil, but it's really less important than Chile and Andes production in general. But it's for Brazil is really important if you consider copper, but the iron is really important globally. Uh, but you have to sum up with the quadrilátero ferrífero that is paleoproterozoic, and we'll talk about it later. So right now we'll talk about the IOCGs, and the IOCGs, as I mentioned, they are we have of those deposits. They are divided in the southern part, southern belt and the northern belt, and this is in the southern belt. But I will talk in general about them, and these are sections of the Igarapé Bahia uh, deposits, and where what we can see are different units of the Igarapé Bahia groups and the Águas Claras formation that is related, and we see their bodies, and their bodies are like breccia, and they have alteration with amphiboles and everything, and these host rocks, they can be different rocks. They can be metavolcanics like mafic, intermediate, acid rocks. They can be amphibolized. They can be iron formation. They can be metagrail so they can be different rocks. But what they have in common, since they are IOCGs, is they have this widespread hydrothermal alteration, as we can see in those pictures here, as we have amphibole and cave feldspar, chloride, and the ore minerals. The amphibole ore can be like the amphiboles. They can be like lunerite, and we have sulfides as chalcopyrite and magnetite. Magnetite oxide, sorry, because we have to have iron oxides, and we have here mainly magnetite, and some of the deposits we have hematite as well, and we have chalcopyrite and chalcocite as the mainly or minerals there. And what we have in Carajás IOCGs in general as well. I'm just taking a picture of Salobo and Garapé deposit here to represent the whole pictures, and I'll see like, and I'll make this with different province because of the time. Sorry. And what you can see here is we have some minerals that they mark like magmatic waters, and others they mark like seawater. And when these are like oxygen isotopes, and when you have like uh, oxygen and hydrogen isotopes combined in different minerals, they show like contribution of volcanic fluids related with formation waters. So this is like the main stuff here. And another authors, they point out the importance of meteoric waters as well. So these metallogenic events here, as we can see here, these events, they took place at the end of the Archean and the beginning. We can see these here and here below, and beginning of the Paleoproterozoic. Uh, and we have like different granites there, but the granites, they didn't help the hydrothermal system, so this work here, Toledo et al. What she shows is like the granites, they were affected by the same hydrothermal event that formed the OCG deposits, and here is a general model that is showing like the Bacaba, Saccharine, Sossego, Alvo 118 deposits. And you can see like the different fluids interacting, and you have similar hydrothermal alteration as you would find in different high OCG deposits in other parts of Brazil and the parts of the world, as you have like calcic and sodic alteration in the deeper part that is represented by Bacaba Saccharine deposits, and you go up that you are represented by Sossego and Alvo 118 deposits. Those deposits, they are close one to another, but they represent different levels of depth in the crust. So uh, you start to have more potassic alteration, more hydrolytic alteration when you go to these deposits. So still in Carajás, we have the iron formation, as I said, Their formations, they are really important if we consider the iron resource globally. And they are related to the Grand Para group. There's part of the Takayama supergroup. And you can see they are like their age, they are 2.7 billion years. So you can see like they are deformed. You have different hydrothermal alterations and supergene alterations. So on, it is not enough to only have their information. You have to have hydrothermal alteration to put more iron and minerals that can release iron when they are weathered. For instance, like iron carbonate and some kinds of amorphous silicas. So here you can see a model that showed like the crushes deposits, hydrothermal fluids. They are like in a shallow level when you compare with Australian and Ukrainian deposits. And their alteration, you have like hematite and calcite, but you have lots of magnetite carbonate as well. And you have kind of amphibole. You can find everything there. But this is more important in Serra Norte deposits. If you go to Serra Sul, you can see more of this stuff. So if you if you consider the whole model that is proposed, is the iron was removed. Here in Caracas, you have like volcanic and air formation. They're associated, but it's not uh, perfectly as Algoma is a little bit different, and because you have like an extensive hydrothermal alteration and the basin is much larger than you have in the Canada. So and then you have in greenstone belts. So what you have is the iron is removed from the mantle from because of the hydrothermal fluid action, and it precipitates because of the interaction with water combined with an oxygenic photosynthesis. So it makes the iron precipitate here. So now we'll talk about the São Francisco Craton that is here in the eastern part of Brazil. We are not talking about the northern part of the continent. And we have the we have most of the deposits. They are related to basement rocks of the São Francisco Craton. There are mostly Archean and Paleoproterozoic. And you have like most Meso and Neoproterozoic. They are covers, and you have in the northern part in Bahia, you have basically three blocks. There are Serrinha, JK, and Gavião. You have Sobradinho, there's a part of Gavião, but they collided in 2.0 billion year to form the Itabuna Southern Crassa belt or orogen, as you would call. And you have in the southern part, you have the Mineral belt when you have the Quadrilátero Ferrífero that is really important to the iron productions combined with Carajás that I just talked about it. But first, we'll talk about the San Francisco crater. So I will start to talk with this area that I studied in my master and my PhD, that is the Cresa Valley, when you have like 300 or more copper mineralized bodies. Uh, the nickel was only found in 4 or 5 bodies, I believe. So it's basically mostly copper and is associated with iron oxides and everything. But it's basically copper sulfides and it's linked to mafic ultramafic bodies. It's basically pyroxenites and you have some minor norites. And you have this disseminated ore that is related to orthomagmatic process. These bodies, they are 2.58 billion years old. And you have a second stage that is related to hydrothermal alteration. In the hydrothermal alteration, you have basically four main types, three types, but I separate because I separate the potassic alteration too here. But I would say you have like the calcic alteration that is mainly dioxide with amphibole, and you have like the sodium alteration that is basically plagioclase with quartz and apatite, and you have potassic alteration. And if you are like in if you don't have much time to interact with the ultramafic rocks, or if you are like far from the ultramafic bodies, you have mostly microclimate. But if the potassium fluids interact with the ultramafic bodies properly, you have phlogopite, and you have like hydrothermal copper mineralization that you have more bornite than chalcopyrite. And but you can have a lot of chalcopyrite, but it's what you have here, you have more magnetite, you have more oxide. And you have like other alterations. You have like calcite veins and quartz veins and barite and a lot of stuff. So this is how the hydrothermal ore occurs, and you can see in everything. And chalcopyrite, and you have like breccia and veins and everything. And the tectonic model shows that we have like these bodies. They intruded in the Neoarchean, and they were metamorphosed in granulite phases in Paleoproterozoic. And after this granulite phase metamorphism, we have like this hydrothermalism that happened in amphibolite ring schist phases conditions. And the I will talk about this hydrothermal alteration, uh, what we have in terms of metallogenic model later. And after this main period here in 1.95 and 1.92, we have a late hydrothermal alteration stage. There is really local, really fissured feeling, and this late stage is related to more oxidized fluids. So here we're talking about metamorphic and magmatic fluids, and in the later stage we are talking about meteoric uh, and seawater fluids. These will be continued as we'll talk about the Paleoproterozoic later. So still in the Archean, in the we have this in the São Francisco Craton, we have the Serra de Jacobina region where we have like chromium deposits. By each stage is leading in production of chromium deposits. It responds for about 70% of chromium deposits in the whole American continent. And we have an important part is from here, from this Campo Formoso region, and we have another is in the Paleoproterozoic part that I will talk just after. And we have another deposits are gold and emeralds and everything. And we have these chromatites. They are related to traumatic bodies. They are basically dunites and peroxenites. These dunites, they are hydrothermally altered to serpentinites. So all of the olivine was converted in serpentine. So we have the main two types of ore is the lump, that is the massive ore, and we have the stratified, they call the fitado. And you can see here in the outcrops as the lump and fitado, they have this interdigitate contact. So these bodies, they were placed in a extension stage in the Mesoarchean, and they were metamorphosed, and they were like uh, mainly folded and folded in some times. They This happened in the Paleoproterozoic, the Triassian. So if we go to the southern part of Bahia, we have the Serra das Águas magnesite and talc deposit. This is are really important, like globally. This is one of the largest reserves of magnesite of the world. And you have like this Archean greenstone belt sequence that is the Brumado greenstone belt. And its line is basically uh, uh, NW uh, hill that is a hill chain that you can go with a lot of different mines of magnesite and talc. And you can see sometimes the magnesite is replaced by talc or is replaced by different states of magnesite, and has an important structural control and everything. So when you talk like about the Paleoproterozoic, uh, here it's worth to cite like the mineral province. If start first talking about the Gondwana, So we talk about the crater, San Francisco crater and the Amazon crater, and I won't have time to mention every single of this one, but to talk about the Curacao Valley and Carajás, uh, and we have like different deposits that we talk about in the Paleoproterozoic, as the Alta Floresta and the Tapajós province here in the Amazon crater. And in São Francisco crater, we talk at the end in the Neoproterozoic, we talk about the carbonate deposits. So if we talk about subcontinents in the Paleoproterozoic, you have different proposals. I will show some of them here. So we have like Colombia and Atlantic are different proposals. So there are some some authors that they consider they are different supercontinents. Some of them they consider they occurred combined, as this was proposed in this model here, as we have like the Atlantica, as we have San Francisco, West Africa, and the Amazon crater is together in Borborema. So basically, the southern platform was basically in the Rio de la Plata was basically the same. And in this model, it is really similar, as we have like the San Francisco crater here, and we have pieces of the Amazon crater here, and have the Rio de la Plata and Borborema province here. So uh, here we have the iron deposits, and it correlates the San Francisco, the Minas Gerais state, with the Australian iron deposits, and we have in Jacobina and Fazenda Brasileira gold deposits. It correlates poorly with some West Africa and everything. And I just talked that I would mention the Curacao Valley again. So I explained that it's really important this to understand like supercontinents and everything, because the collision it formed a OCG style alteration, as the ultramafic bodies they if you go towards the north, if you see more sodic alteration, it gets more scarce, and you start to see more potassic with phlogopite alteration, and then hydrolytic with barite alteration. And when you see more phlogopite biotite, you see more hydrothermal ore. So this when I study like the region beyond these deposits, other regions closed, it was clear that this collision, it was important regional, and we consider different granite belts. So it was really improbable that the San Francisco crater was together with the western of the Amazon crater, and like West Africa at that time, so it was probably just related with Borborema, because the Curaçao Valley, it will have like similar deposits that you can find in Borborema province, with IOCG and another features as well. So this model is a possibly model to consider, like in the Paleoproteros. Like this model was proposed by the Grella Filho and his collaborators in two different occasions, and we just adapt to put like the granite belts and mineral deposits, and this reef sequence here. There's the Rusalitry that I won't get too deep here. So there's another idea about the San Francisco crater in Paleoproterozoic. So still in San Francisco crater, we have like these gold deposits that they are related to the Greenstone Belt, the Rio Itapicuru, and is the name says the Greenstone Belt. We have like in the northern part, they are mainly hosted by acid volcanics and graphite schists, and in the southern part, they are related to quartz veins hosted by metamorphic volcanic rocks. So what you can see here is a geological section of the southern part, when you have the massive volcanic with gabbros, and this alteration zone with breccia and quartz veins. Uh, and here is you see native gold. and these quartz veins, they have tourmaline and everything. And this greenstone belt is a paleoproterozoic greenstone belt that is originated as a collision of the small continent close to Serrinha block that is there in the northern part of the San Francisco crater. Okay, I was worried because it's appearing reconnecting of my translation. Okay, I believe it's working now. Okay, okay. So we have the other important deposits that is in the Serra Jacobina region. That is the region that I mentioned that is close to the Campo Formoso intrusion. The Campo Formoso is in this region, and here in the Jacobina you have this in this yellowish tones. You have this sedimentary sequence that is basically clastic and is basically uh, quartz, quartzites and quartz conglomerates, and you have minor metapelites. So what you have here, you can see some of the ore with pyrite, and you have cersite and quartz in those quartz-rich rock. And there you have four different types of ore. The first one, it is hosted by the metal conglomerate. Is like a paleoplacer deposit. And then you have another deposits that are related to hydrothermal alteration in mafic dikes and then ultramafic rocks. And finally, hydrothermal alteration with sulfides and everything in veins, quartz veins, related to quartzites. So you have a sedimentary, and then you have a superimposed hydrothermal model. So we also have in the paleoproterozoic of the in the San Francisco crater, you have the Maracas vanadium deposits that is in the southern part. Maracas is the name of the place, and you have these multiple intrusions. They are like 2.2 billion years old, and you have like pyroxenites and magnetite pyroxenites, and the magnetites, they are the mainly ore. So you have here in my hand, you can see like 100% magnetite, and this magnetite, it can hold up to 5% of vanadium, V2O5. So here, when you use like the FRX, you can see here you're about 0.9%. 0.9 corresponds about 3.2. There is a really high grade of V2O5. And here you can see the magnetites in the outcrops. You also have related to traumatic rocks there in southern Bahia. You have sulfide hosted, uh, you have ultramafic hosted sulfide nickel deposits, nickel, copper, PGE deposits. They are called the Mirabella deposits. And areas, they are in the Itabuna-Soldado Curaçao belt. And they are related to dunite and Harsb. And after you have dunite, and after you start to have pyroxene, so you have harbuzite, olivine orthoperoxenite or orthoperoxenite, and you start to have less, like the gabbronorite, you don't have the sulfide. So you have basically in the pyroxene-rich magmatic layers, the dunite, the harbuzite, the orthoperoxenite, and the olivine orthoperoxenite. So these are the rocks. Okay, you can see the ore here in hosted by orthoperoxenite, and the ore is basically pentlandite, pyrite, pyrrhotite, and chalcopyrite. And also related to traumatic rocks in the in a paleoproterozoic granulite facies in a paleoproterozoic collision, but this is close to the Serrinha block. You have the Jacuruci complex. So we talk about the Campo Formoso intrusion, and now we're talking about Jacuruci. Is paleoproterozoic is 2.08 billion years old. So you have like basically a huge chunk of chromitite is one single layer that is maybe folded or folded, and you can see this chromatite that is basically in this layer, and it's massive. as you can see in these outcrops, and you have some disseminated there. So we also have ores related to the sedimentary sequence. So we have paleoproterozoic phosphates. They are related uh, basically to the Itabunas saurogen, and we have related to the Rio Salitre and Rio Salitre complex, and you have in the Jacuzzi Valley we just talked. We have related in the host rocks of the intrusions. There are sedimentary. We have these phosphates. They are related to important carbon isotope change, and they are basically epithet related to carbonate rocks. As we can see here, we have like marble and everything, and this is like ammonium molybdenite that is like a test for phosphate you do in field, and it's not exciting when you see it doesn't have much beautiful grades, but when you have hydrothermal alteration, you can see like this beautiful apatite crystals. And here you have the isotope, the carbon 13 isotope signature that is, it marks a change that it happens between 2.2 or in 2.1 billion years old. That is, it's called the Lumagundi Jatuli isotope change. And we can see here in this place. And this was like the geotectonic reconstruction. I made this figure. I was co-author, one of the co-author of this article that is really interesting. You should read it. It's really interesting. And you usually have phosphate related to iron, are minor iron occurrence, and graphite as well. So regarding graphite, this is a master thesis of a student that is doing PhD with me. He did his master with Professor Odomizi, that was my supervisor as well. And his was his master. His name is Ibi Camera. Was he studied the graphite deposits, graphite occurrence, I would say, mineralization related to the same unit to the Tectonics rocks. And you have like graphite bearing schists, and they are closely related to those phosphate occurrence. They are like close, literally close. And you have different types of graphite, and basically you have like sedimentary signatures indicating an subox, 2-ox, and signature, but you have more than that, you have a lot of metamorphism and hydrothermal remobilization. So you have different types, 3 or 4 different types, different of your interpretation. You have different types of ore, okay? Because you have sedimentary and have metamorphosed, so you can interpret as different types or just one. So if we go south to the southern part of the San Francisco Craton in Minas Gerais state, we have the iron quadrangle deposits, the quadrilateral ferrífero deposits. So this is really important. It was a major iron producer long before Carajás was discovered. So it's historical, is really important. And you have most of the information are related to the Cauê formation of the supergroup of the Minas supergroup. So you can see like the Minas supergroup and the Cauê formation is here marked in black. And we'll talk about the Águas Claras mine made mainly. This is this one here. Okay. So regarding the stratigraphy, we have 2 different types of iron formations. The first one is related to the Rio das Velhas supergroup, is Algoma type, but it was never produced for iron, just for gold, for load gold, but it's paleoproterozoic load gold. And here we have the important for iron producers, the Cauê formation. But as I said, the Cauê formation, you need to be deformed, you have to have hydrothermal alteration and weathered to have a real economic potential. And you can see here in these pictures, you can see different types of iron formation. You can see some of them have dolomite, iron dolomite, and when weathered, this iron dolomite leaves the carbonate and it only stands with iron, so it's enhanced the iron grades. So we also have Imperium Proterozoic. So jumping from the San Francisco Craton to the Amazon Craton, we have two really important gold producer provinces. There are the Alta Floresta Gold Province that is here in Mato Grosso State, where I live. That is here. It calls some authors as those authors here. They call the Juruena Mineral Province as well, but I call the Alta Floresta. And we have also the Tapajós Mineral Province here. Okay, they are really similar. They are paleoproterozoic. They are related to granites and volcanics. They have signatures of porphyry systems and epithermal systems, and they are basically separated by this Cachimbo Ridge here. So we have different geological sections representing. So you can see this is in Tapajós, but it's also representing what we see in Alta Floresta. And what you can see is basically different kinds of granites and volcanic rocks, and they are including one of another. They have different uh, age ranges, and in Tapajós, I would say they predominate about 2.2, 2.0, and in Alta Floresta from 2.1 to 1.88. So it's Alta Floresta is a little bit younger, but they are related to like granites, basically calc-alkaline granites and volcanics, and you have hydrothermal systems. And some of them they are more close to porphyry with K-field spar, and you have like chlorite, you have propylitic alteration, and others are related to more epithermal features with alunite, and they are usually they have sulfides. The gold are related with sulfides and can be associated with copper and molybdenite. So this model shows what is seen in Tapajós, and as I said, is similar to other forests, but we have is like porphyries, different porphyry gold and porphyry copper, and they have like thermal veins. Those deposits, I must mention, it really they are really different from what you see in Phanerozoic in Andes in the Andean chain because they are much smaller and usually they have higher grades, but they have the same hydrothermal alteration and the same, I would say, mineralogy, both hydrothermal and or mineralogy. So here in Alta Floresta, you can see like potassic alteration and you can see like propylitic alteration and sulfides and gold is included in sulfides and their age in Alta Floresta, although you have like much older rocks, most of the deposits dated by uranium osmium in molybdenite, they are about 1.78 billion year old. So this model here, it puts a lot of those deposits we just seen in like geotectonic events. So we have like we have ultramafic magmatism there in San Francisco Craton, and then there's Caraíba, and then we start to have like the ocean, the felsic magmatism alkaline that they are like some of the I would say the Tapajós, oldest Tapajós deposits could be included here, and then have a lot of those Amazon craton we just seeded. We have the golden on mine Guyana. I didn't see it because I don't have time. I just almost running out of time. You have so much stuff to talk, and we have like golden Jacobina, and I just talk, and we have like autoflora, like stuff that are younger, and I would talk about more different deposits. So the Mesoproterozoic is not so important if we consider metallogenic. This reconstruction here, it shows what happened to made happen with San Francisco Craton because Amazon Craton, it has the Sunsas In the Rondônia Juruena province, you have like part of the Greenvillian cycle, but in San Francisco you don't have. You have in the Borborema, you have in Borborema province, they call the Carreiras Velho cycle. But in San Francisco, as in the Rio de la Plata, was they were if islands. They were not colliding with other continents. So we have like this expression boring billion for those who study gold, orogenic gold deposits. So this was not so boring in here in the Amazon Craton, because here in Mato Grosso we have this Alto Guaporé gold province is in Mato Grosso, and we have the Sunsas gold province in Bolivia as well. Is about the same what I will present to you, but you can see here the Sunsas belt is in Bolivia, but we'll talk here about the Aguapeí belt that is, and the Nova Brasilândia belt. They are the Greenvillian belts related to Rodinia supercontinent here in the crater. So we you have this sedimentary sequence. There was like a rift. It was deposited in a rift, and we have like conglomerates and quartzites and schists and everything, and its metamorphosis is really deformed, and we have this age here. So the age is like about 1.1 of the sequence, and the mineralization is just about new Proterozoic and everything. So you can see here the stratigraphy, and you have four different types. Basically, you have like the lower trap that is related to a fault in the basement rocks. Uh, then you have the middle trap that is related to metaconglomerate. Then you have the upper trap that is related to schists, and then you have the bonus trap that are like quartz veins in the upper meta sandstone. Okay, so you have this this map. It represents what we can see there. So you have different. You can see you have different dome and basing structures, and you have the gold is related to veins that are confined to those layers that I just mentioned. So you can see these different veins. There's basically quartz cerussite, and sometimes with hematite or specularite. You can see there's structural control here. It depends on which mine you're looking at. You have different control. And here the grades are modeled. This was the master by Mariana Malheiros. It was under my supervision. This is her article that is in submission for the Geological Society of London. And you can see the gold grades, and she modeled the structures and everything. You can see how they are changed because of different here are veins in here are the main structure. They are related to change in the paleo. So basically you have the structural evolution when you start with oblique convergence is NNESSW, and then we have a rotation of the vector, the transpection vector, and is now the collision is now oblique and is still, and it's a transpection, and it's NESW, and you have like a second generation of quartz vein. Those first two generations, they are like important, and you have like late generation that is bearing, and you can see like how it's associated to the Rodinia paleocontinent, and you have this collision with the Laurentia continent that was responsible for to all this structural evolution that I mentioned. So we have this Rondonian tin deposit that is in Rondonian states. They're related to these intrusions that is they are between the Meso and the New Proterozoic. You have those, one of those that some of those they are older, but this example here is it enters in New Proterozoic, and you can see here you have like Azo risings. They are related with casterite. That is basically, you can see here the casterite rich layers here. There's these dark minerals, And casterite is precipitating stage 3 and 4 related to quartz, microcline, albite, cerussite, but you have like white mica and topaz and fluorite and everything. And they're related to magmatic fluids interacting with meteoric fluids that is typical with rising deposits. And then we finally go to the new petroleum. Like we are getting there. People are you have to must have faith that we are get there. We are getting at the end. So we have like this new Proterozoic sequence. They are mostly carbonate sequence, and they host different deposits. They host lead, zinc, barium, fluoride, phosphate deposits. I will talk about some of them. I will talk about the Ursa Basin in Bahia. There you have lead, zinc, and you have phosphate deposits. But I'll talk firstly about the phosphate deposits. And in stratigraphy, they are pretty the same layer. They are these dolomites and everything. Uh, but before it started with like a most oxidized moment of the basin, and then you have a late hydrothermal fluids that interact with those oxidized layers and precipitate the lead iron, the lead zinc deposit. So the phosphates are related to stromatolite, they're related to biogenic activity, and you have different fluids that interact, and the fluids they get radioactive elements, and the lead is from there. So the lead is from uranium and thorium decay that come from the basement rocks. So you also have in the southern part of Bahia, northern part of Minas Gerais, you have fluoride and lead zinc sulfide as well. So they are related to collapse breccia. They although they resemble Mississippi Valley deposits, they are more related to Sidex type, Irish type deposits. So you can see those in this carbonate sequence here. You can see sphalerite and you can see fluorite. So sphalerite is like zinc, yeah, and fluoride, zinc sulfide and fluoride. They are really hydrothermal. In the new Proterozoic, you have the only kimberlite hosted diamond mine in South America, and the only one outside Canada. Basically, in our continent, you have Canada and this region that is in Bahia, there is Brauna kimberlite that produce diamonds. But those kimberlites, although most of the kimberlites in Brazil are Cretaceous or Phanerozoic or Paleozoic, the only mine comes from Neoproterozoic kimberlite. So this brown kimberlite, you have different bodies. It is the mine started here, but they started producing different bodies now. And as a kimberlite, you can see like those those features typical of kimberlite, volcanic features. You'll see phlogopite here with vitreous vitric features. You have olivine replaced by serpentine, and you have like lichen, clinopyroxene, and everything. And here you can see the age is 641 million years old. And in his model, you can see like the you have this wall rock that is Paleoproterozoic to Archean, and the kimberlite. It was originating in the mantle. It always is like kimberlite and carbonatite. They always come from the mantle. So, but they estimated their depth in about 150 kilometers, and they came there and they have like pipes and blows and dikes, and all of them host diamonds. And having new Proterozoic in southern Bahia, we have this uranium province. It's the most important uranium province in our the South America continent, and in Brazil, obviously. And it new Proterozoic, but its history started in the Paleoproterozoic. So we have this 1.8, 1.75 intrusions. They are granites, and they are deformed and metasomatized. They underwent hydrothermal alteration, and the mainly hydrothermal alteration is albite, and this albite, it produces albertites, and they have like granite and related to hematite because they are oxidized fluids, and they have this ore, when they are weathered, they form uranofan, that is weathering uranium mineral. So you have the as I mentioned, those granites, they were placed in 1.7, and then you have forest metasomatism in 1.0, and then you have a final metasomatism in 600 million years old in the Brazilian cycle. So I must mention the lithium in Brazil. The most important places is Minas Gerais, there's the Jequitinhonha Valley, and they're related to pegmatites, related to basically S-type granites. They're including metasedimentary rocks there, and you have produced the production. It's basically from spodumene and petalite and lepidolite. So you can see just those giant, like 3.5 meter spodumene crystal here, and here you can see petalite, pegmatites, and you also have a lithium um, related to tourmaline and other gemstones there in Borborema province. I'm talking here about Paraíba and Rio Grande do Norte states, but you also have in Ceará states as well. In Ceará states, you have phosphate. I have a student of mine, Ramon. He's doing his PhD there, studying this lithium phosphate hosted deposits hosted by pegmatites. And but I'll talk today about those one that were studied by the Brazilian Geological Survey before. This province that this project that I just mentioned it's related to Brazilian Geological Service as well. And you can see those some pictures of one of those artisanal mines of the garimpos, as we call here in Brazil, and you can see like the pegmatite with a lot of platy muscovite, and here you can see lepidolite is green here, and this is albite replacement. And here you can see spodumene here that is really well developed. And these schematic sections show here is a zoned pegmatite. There is capoeira 2 is the name of the pegmatite, but as you can see there is a center zone with quartz and spodumene, and you have like albite and calcite spot bar, and you have tourmaline that is revite, and you have granite that is spessartite. So here's the main Neoproterozoic events as summarized. So uh, yeah, as I said, Mesoproterozoic is not that important, but in Neoproterozoic you have a lot of stuff happening with the Neoproterozoic carbonate sequence, and in Borborema province we have those pegmatites, as we have in Minas Gerais as well, and we have those I didn't mention, but I have different gold deposits that were formed in Europatrozoic, and the uranium is really important as well. So the tectonic cycles. Now we are reaching the Phanerozoics. I almost even getting there. Please don't don't abandon the transmission. I was getting there. Sorry for breaking up the time, but it was a lot of stuff to talk, and I want to talk about the Phanerozoic as well. So, as I said to you, we have probably some proto-cratons or proto-supercraton there with Volbara and Superia, or mainly they were not linked at all. We have multiple models there for Archean, and there in Paleoproterozoic, I showed you like Columbia, Atlantica, multiple cratons, and here is Nuna is another model for Paleoproterozoic, and Rodinia is in Mesoproterozoic. We know that Rodinia is important, and the Amazon craton was involved, as I just showed. And we talk about the Federals like Pangea is a consensus. Everyone that knows how Pangea looked like. You don't have much to change, just basically its trajectory. So you know that South America was linked to Africa and Caribbean. was formed by the collision of North America with Northern Africa. And what we'll talk about is first the Andean porphyry copper deposit. So as I just mentioned in the beginning of the presentation, the Andes are the main copper producers of the world. As I would say, like Chile, but Argentina is really important as well, and Ecuador and Peru, it has a huge potential. And its copper comes mainly from copper deposits, but also you have some deposits that are more close to IOCG types deposits. So I'll talk first about the porphyries, and those porphyries they are related to epithermal deposits. That is you have more gold and silver, but you also have copper, and later I'll talk about the LCG. So you have those different copper deposits. This work here is really interesting. This is by Silito and Perolo. Silito is one of the probably everyone who studies porphyry deposits knows about him. He's a really outstanding researcher. And in this study, it shows different porphyry deposits that you have like recurrent mineralization. So you have Paleozoic rocks and you have Miocene and Pliocene. So mineralization. So you have two events of magmatism and sometimes two events of uh, porphyry mineralization. So it's those numbers here are like the oldest ages, like the Paleozoic and everything. And you can see some of younger mineralizations here. There are like Eocene and Pliocene and everything. So here you can see those ages here. You can see like Permian, Carboniferous, like yeah, as I said, the Paleozoic ages from those deposits. I will talk about this filo the salt that is between Chile and Argentina to represent. And you can see you have those reactivations here in Neogene and like Paleogen and Neogene. So what you have here, you have like relatively thin crust when you have like at the end of the Gondwana, and you start to have a crystal extension at the Jurassic. But you know, like the terrain was really only modified as at the end of the Cretaceous when we were talking about the Andes. But we have this probably what they say the same place what the authors interpret they were displaced worked as a fluid conduct to the hydrothermal fluids to enter those structures. They are mineralized two times, and the magmas and the hydrothermal fluids they flowed there two times. Okay, the first in the Paleozoic Triassic and the one in the Cenozoic. So here in the we have those porphyry epithermal system, the Philadelphia mineralization that is in Chile and Argentina that I just said. So you can see the map here. You can see that it's really close to the border. And here in this picture, you can see a lithocap with you can see a lot of malachite that is copper carbonate from weathered copper sulfide ore. So we have here the geological map and geological section where we can see, as I said, you have all these Permian rocks, and you have Miocene Quaternary. Here is just colluvial rocks, but we have younger magmatic hydrothermal system that cut those rocks here as well. So, in as we would expect in porphyry thermal deposits, we have basically a magmatic system with some intrusions and then a lot of volcanic rocks. So here we can see some mineralization with some textures that we would expect to see in porphyry. This like A to D here, and then we have This wood is expecting more in epithermal. So we have a chalcopyrite, pyrite related to breccia and replacements and banded fangs with potassic alteration. And here are the supergene products. So the weathered ore. So we have those beautiful copper bearing minerals. Okay, it's oh my god, it's networking problem. No, okay, so it's appearing here that I have a network problem. Okay, okay, thank you. So we have like chalcocite, and we have uh, malachite and cuprite, and we have different minerals. And this is cocumbite, that is a copper silicate. And in this model, we can see firstly from the middle Cretaceous, when you have like when the engine orogeny buildup was being setted. So this, as I said, in the Cretaceous was the ends starts to rise up as orogeny. So we form first porphyry copper, that is the La Fortuna Flamenco, and then we have the Filo del Sol porphyry. And here you can see these different magmatic episodes represented. And here is representing the evolution of the Filo del Sol, that is, as I said, that is Cenozoic, is although the host rocks are Paleozoic, this deposit is really young. So we have like the intrusion, uh, and we form the epithermal. First, we form in depth. We form porphyry deposit, and then in shallower portions, we form epithermal that is more rich in gold. And then we have IOCGs in Andes as well. That is those triangles here. As Candelaria is the one that we'll talk about. And this is just, and I'm just talking about this to represent. So it's related also to lavas, to calcocaline magmatism, volcanism in Andes. And as in IOCG deposits, we see uh, potassic alteration, sodic alteration, iron oxides, sulfides as chalcopyrite, pyrite. We see in the calcium alteration, amphibolites, we see here a shear zone showing the structural control of the alteration, magnetite. They are related, closely related to iron apatite occurrences and deposits as well. And you can see here in the stratigraphy, their ages are considered to be Albian to Aptian, that would be early Cretaceous, about 114 million years. So it was dated by Argonio. Okay. And it's important to mention Brazil carbonatite hosted deposit to have niobium, titanium. I put in Portuguese. Is rare earth deposits, not EGRs, REE, and phosphate. So the most important are related to the Alto Paranaíba province, that is in Minas Gerais and Goiás states. I will talk about Catalan, that is in Goiás states. Is early is early Cretaceous. It's not early. It's late Cretaceous is 85 million years, and you have this carbonatite, where you have carbonate rocks with phlogopite and olivine and everything, and the main ore mineral is pyrochlore. And you also have phosphate that we find in São Paulo state, that is called Jacupiranga, is older. So it's important to mention this. We have this theory that kimberlite and carbonatite, they form a single alignment. It this work from here to here, that it was like the hot spot that formed one island here, the Tristão da Cunha Island. But those on here, they are much older, they are Paleozoic. So it works with some intrusions and for the carbonatite, but not for Jacupiranga. Jacupiranga is older because those intrusions, there are 85 to 70 million, and Jacupiranga is 131, 133 million years old. So this carbonatite, they have appetite, and they are veins, they are disseminated, and here you can see disseminated, and they have replacement ore. We also have in Brazil kimberlite and diamond areas. I will not detail that much, but you can see like the kimberlite fields is here, those black spots here. Okay, those black stains here, and you can see different diamond producing areas. The brownest here is Neoproterozoic. So we talk about the ages. Most of them, the most important, they are Mesozoic. Okay, basic Cretaceous, and you have those in Rondônia state. They are Paleozoic. But the main producer is Neoproterozoic, and you have some Mesoproterozoic here in the countryside of Bahia. Here you can see those ages. This map is really distorted. It was not supposed to be that distorted, but you can see those ages I mentioned. You have Paleozoic here, and you have some early Cretaceous here, and you have some late Cretaceous here, and some Neo and Mesoproterozoic here. Okay, so most of those kimberlites have, they host diamonds, and they have associated placer deposits, but not all the placer deposits are associated with the kimberlite. This was the one I studied. It calls it Chiquita. It's in southern Mato Grosso state, the state that I live, and you don't have kimberlite, you just have diamonds in the river, and in the river it has a strong structural control. Those meanders, those curves, they are controlled by those faults, and you can see those pictures here, and you have some cut and fill channels, and those are the diamonds, and they are sculpted in the bedrock. And those are the different types of traps you'll find here. You'll find the point bar that are related to point bar or rivers. You have the cutting field channel. You have those pockets that are those small falls you have, and the potholes that are those semicircular holes you have in the bedrock. And diamonds are represented here. And in Phanerozoic, you also have important laterite deposits, and I will talk specifically about the Pará-Maranhão bauxite province that is the most important in Brazil. That is, this province is between Pará and Maranhão states. Maranhão is in northeastern region, and Pará in the northern region in Brazil. So the bauxite is related to sedimentary rocks. It's really rare, but the weathering there is so strong that you have the weathering over sedimentary rocks. There are like sandstones and shales, and you can yield bauxite. So you have this geomorphological control that you can see here, this physiographic control that you can see. You have this really kind of, you have these planouts there, and this those with these plain tops, you have those plateaus with bauxite, and you can see here the sandstone, and you have different types of bauxite. This is like what they call the structure bauxite, that you can see some structure of the sandstone, and this is the massive bauxite, and here's the nodora bauxite. So what can we conclude? The Archean deposits are concentrated in Brazilian kratom. So although you have some kratom in other countries, they don't have Archean deposits. You have iron, IOCGs, copper, chromium. The Proterozoic cover a huge diversity of mineral deposits. Most of them are Paleo and Neoproterozoic. You have like iron formation, IOCGs, iron, copper, porphyry, thermal, phosphate, orogenic gold, lithium, gemstones, diamonds. You have different stuff. going on there. Don't have much stuff in Mesoproterozoic, basically team, and the Phanerozoic metallogeny is strongly linked to the Andes. The Andean chain is the most important if you are considering porphyry, thermal, and IOCGs. And you have alkaline intrusions, placer and laterite deposits in Brazil. Besides bauxite, you have laterite nickel that I didn't mention, but you have all of this diversity in the South America. So thank you for our time. Thank you for your patience. And if you have questions, just make me know. Thank
Yeah, sure. Sure. Thank you, Professor Pedro. That was an excellent presentation.
you.
Really interesting deposits that you have there in Brazil. Some of them are really new for me. I really like it. So we have some questions in the chat.
Okay.
I will read it for you. So the first question is from Andres. What are the main type of ore deposits found in the Carajás mineral province?
Yeah, I would say the main type, you have those. Thank you for the question. Firstly, Andres, thank you for the question. We have different those two different groups. You have the iron formations, so the iron ore that is hosted by iron formation, but it's not only the iron formation, as is the hydrothermal enrichment. And you have the IOCG deposits that they span from Archean to the prior Proterozoic. So you have those different groups. But globally, the iron deposits are the most important. But for the country, the copper deposits are really important as well.
Okay, thank you. Another question from Andrea. Thank you for your presentation, Professor Pedro. How does the quadrilateral ferrífero compare to other global iron ore districts in terms of size, grade, and geological setting?
Thank you, Andrea. That was a nice question. So the the reserves you have the most important. You have Brazilian, Australian, and South African deposits, and the quadrilateral ferrífero is one of them. And all of those deposits that are the most important. So the reserves they change. So right now the quadrilateral ferrífero ranks in third in reserves, but in second in production, it sums up with Carajás. But it ranks seconds in reserves. The first one is Australia, is Hammersley. But all of those three provinces, they are Paleoproterozoic. They are Lake Superior type. They are related to sedimentary environment rather than volcanic related iron formation. Volcanic related, that is we call Goma, is not that much important in terms of size, excluding Carajás. Carajás is important volcanic related, but it's not Algoma. Carajás is a different type. Carajás is Carajás.
Okay, there's another question from Jose. Yeah, I was about to ask also this. How do cratonic margins differ from cratonic cores in
Oh,
terms
that's
of mineral
interesting.
potential?
Interesting question, Jose. Thank you. So usually cratonic cores, they are older, and cratonic margins, they are younger. So when you are talking about older tectonics, you are talking about more greenstone belt related metallogeny. So you would expect to see more VMS. We don't have much in South America VMS, but I'm saying like globally in North America, Canada mainly, and but in Brazil we have, and in Bolivia we have lots of gold, and in Guianas we have lots of gold, load gold, orogenic gold, and related to greenstone belts. And we have also iron formations. So I would say iron and manganese deposits. And when we start to go towards the margins, you have more intrusion related mineralizations, not gold intrusion related, but intrusion related in a broader sense, like tin and skarns, grisings, and porphyries and epithermal and everything. and you have load golden events. Every place you have collision, you have load
Okay,
gold.
okay, the next question is also related to greenstone belts. So Daniel asks, how do greenstone belts within craters
Yeah,
relate to
thank you,
mineralization?
Daniel. So uh, the Greenstone belts is a kind of cake recipe. You have a recipe to have a greenstone belt. In the recipe, you have to have oceanic crust. If you are in the Archean, it has to have comatites. And if you are in the Paleoproterozoic, you have tholeiitic basalt. And then you have iron formation, and you have archetype volcanism, calcalcaline volcanism, and you have classic sedimentary sequence. And greenstone belts can have VMS, can have load gold, can have iron formation, algoma type. If you are talking about the Archean, if you are talking about Paleoproterozoic, you can have phosphate mineralization. You can have porphyry because you have intrusion and you have volcanism. You can have porphyry mineralization as well. So yeah, you can have all of those types. I believe I didn't forget anyone, any type. So you have.
Okay, there's another question about the quadrilateral peripheral. What is the relationship between banded iron formations and cratonic
So
environments?
thank you, Andres. You have iron formations. If you are talking specifically about iron formations, not iron ore in general, but iron formation, you have three episodes, and they are one is Archean, that is the Algoma that I mentioned. Another is Paleoproterozoic, that is Lake Superior, that I mentioned, and they have another one that is Neoproterozoic, that is Reptan. That is not that important in terms of size and production, but they are all of them are Proterozoic. The Neoproterozoic is not much related to Cratons, so we are talking about more about Archean Paleoproterozoic. So they are directly linked because you have to have Cratons to have Archean terrains and Paleoproterozoic terrain. Even if you don't have Craton, you have like reworked Craton. They used to be Cratons. In some time they were Cratons. So you have to have all these terrains to have Archean Paleoproterozoic rocks. And why iron is related? Because at the time the Archean Paleoproterozoic, the Earth was hotter, so you have more heat to put the iron out of the mantle into the ocean. So yeah, I would say this would be the explanation, the relation.
Okay, thank you. There's also some greetings from Victor Arruda.
Mhm.
Greetings to Professor Pedro. Geologist Victor Gabriel from the
Greetings,
Federal
Victor.
University
Thank
of
you.
Mato Grosso. Send you some greetings. Now, Carlos asks, what types of geological data are used to reconstruct ancient continents and
That
supercontinents? Like the diagrams you show us.
that's really good. That's really good, Carlos. Thank you for. Yeah. So if you look like the oldest paper as like the Teixeira paper that I mentioned, 2007, 2010, and Zhao 2002, it was amazing. The guys they used to do solely by their geological knowledge. So they did as a puzzle and they put everything together. It was amazing work the guys did at the time, but after the 2010s, the works they started to use more and more paleomagnetic data, but not everyone, not everyone, how would say that, trust this data. But paleomagnetic, basically, you go there, you find dikes like math dikes, and you take out a sample of the dike, and you make like geochronological analysis, so you know the age of the dike. And besides that, the paleomagnetic is because like humanite, magnetite, and magnetic minerals, and you can see their orientation, and their orientation is related to how close they are to the pole or to the equator. So because of that, the guys can know, okay, at this dike has this age, and the magnetite was that close to the equator or that close to the pole, and they can reconstruct the continent. So this is basically what they use. But the mineral deposits, they play a crucial role in those oldest reconstructions, and they are really important because they have to match, because you have similar metallogeny. As I showed to you, you have huge province as Andes and Carajás and Quadrilátero Ferrífero and Curaçá Valley. So when you enter to a different craton, but they used to be the same craton, you have to have continuity in this mineral province. So they are useful.
Okay, yeah, we're about to
Okay.
finish, so just a couple of questions. One from Victor about the Alta Floresta Gold Province. What is the role of hydrothermal alterations in the region's
Thank you,
deposits?
Victor. The Alta Floresta Gold Province, as Tapajós, they are a porphyry thermal system. So this porphyry thermal systems, they have potassic alteration, that is have K feldspar with biotite, and then when you have more thermal, you have more argillic alteration with clay, as the one that you study. You have like the argillic alteration. Victor does his masters with me, and he studied thermal like deposits, and these alterations, they are the result of the interaction between the hydrothermal fluids with the host rocks. So they transform the mineralogy of the host rocks, and this transformation is part of the process that allows the ore minerals to precipitate. Many factors can play an important role. The many factors are really important in explaining how these fluids can precipitate. So you can have fluid mixing, you can have boiling, you can have decreasing of temperature, but the interaction of fluids with the host rocks or the hydrothermal alteration is is plays a crucial role in making this precipitate.
Okay, well, just two more questions. Another one came up lately. So from Argemiro, well, he made a correction. What do you think about correlation between, I think, Bambui group and the carbonates from
Okay, thank
Iresi?
you, Jamiro. This for the question. The Estancia group is in the Sergipano belt, that is in the Borborema province. So is a new Proterozoic. Is, as I just mentioned, is a continuation of the San Francisco crater, that is the IRC. So they are pretty similar, but they have difference because the Estancia group was in the margin, so it has more features of glacier marine deposition, but the metallogeny is different because the Estancia group, it hosts copper deposits, copper occurrence. It's not deposit, copper mineralization instead of lead zinc. So it's different.
Okay, and the last question from Goyo. What difference are there between banded iron formations in Western Australia and Brazil? Why
Thank
are they
you,
bigger than
Goyo.
Brazilian?
Actually, individually, I would say Brazil has bigger, larger deposits, but collectively, if you consider the whole province, Australia has more iron, as I answered earlier today. But what happens? Australia, you have more area, so you have more iron formation. But in Brazil, if you consider each deposit individually, you have more hydrothermal alteration, and you have more combined weathering. So supergene deposits are really important in Brazil. Actually, every iron deposit must have supergene alteration. You have to have weathering. So the start of a iron mine is the weather, the supergene removal of silica to get the iron formation more. uh, a, a higher iron grade to enhance their grade. So Brazil has this tropical climate that Australia has as well, but Brazil is closer to equator line and has Amazon, and even Minas Gerais has a really hot and humid weather that you can measure that have you can measure how weathering is important in Brazil, that will have caves in iron formation that is pretty rare. In Carajás is the only place in the world that is have speleothems, that is like stalactites, stalagmites. You have this in iron formation. It's really rare. So this weathering hydrothermal is important in Brazil.
Okay, thank you everyone for all the questions. So just to conclude, I want
Okay,
to
then
also
let
share
me
my
stop
screen.
sharing mine.
Okay, maybe you can see it now.
Thank you.
Yep, I think you can see it. Okay, Professor Pedro, on behalf of the SEG student chapter, we sincerely thank you for sharing your expertise with us today, and we truly appreciate your time in contributing to our academic formation. And as a token of our gratitude, we would like to present this certificate of appreciation, which reflects our deep respect for your contribution to our chapter. Once again, thank you for being with us today, and we look forward to staying
Thank you,
in touch
Stalin.
and hope to
You can
welcome you
count on
again
me if
in
you
the
need
future.
anything, and
Thank
send me
you,
this
Professor
by
Oka.
mail, please. Okay? Thank you.
Okay, sure.
Feliz
And
Pascua.
also, thank you everyone for your time and questions. Thank you. Yeah. Igualmente, gracias. Hasta luego.